Hi all, welcome to this lecture 5 of Unconstrained Optimization lecture series. Today we are going to discuss on one-dimensional optimization algorithms. So before continuing with the lecture, let's see what we discussed in our previous few lectures. So in the last lecture, we discussed some necessary and sufficient conditions for optimality. So first of all, we discussed first order necessary condition, which said that if some point x star is a local minimum, then the derivative of the function at that point is zero. We also saw that this is not a sufficient condition. So let's say you find derivative to be zero, that does not mean that point is a local minima. Then we also talked about the second order necessary conditions, which said that if some point x star is a local minima, then first derivative and the second first derivative should be zero at that point, and the second derivative at that point should be non-negative. That's what is said. But we also saw that this is not sufficient, which means that if we find a point where f dash, if first derivative at that point is zero and the second derivative is non-negative, then it does not mean that that point is necessarily local minima. Then there was second order sufficient conditions, uh, which said if we find a point where first derivative is zero and second derivative is positive, then it's definitely a local minima. But this is not necessary, which means that if there is a local minima, then this may not be true. That is, first derivative is zero and second derivative is a positive. This may not be true. So then we finally came to sufficient and necessary conditions for the function. So let's say we have a sequence of derivative, that is at some point first order, second order, third order, and kth order, and so on. Then the first non-zero derivative, let's say some first non-zero derivative, let's say f k x star is non-zero. Before this, that is from 1 to k minus 1, all the derivatives are 0. Then if k is even and is positive, that is f k at x star is positive, then x star is a local minimum, and then this is a necessary and sufficient condition. So and this is what our discussion was, and at the end we also discussed why the algos are necessary, because we thought that based on these conditions we just find the first derivative, see the stationary points, then at that point look at these sequence of derivatives and see if it is a local minima or not a minima, or etc. uh, then why, if there is an analytical solution, why do we need algorithms? So the answer to that question is the first and the foremost thing we have to solve is the first derivative equal to zero. This can be an equation whose analytical solution does not exist, or you cannot find a solution analytically. So that's why we need algorithms. So with that recall, let's start with our lecture today, and let's define what we'll let's down what we learn today, what type of algorithm we learn today. So uh, types of algorithms. So first type of algorithm that we'll learn is derivative free. Second type we'll learn will be uh, derivative based methods. Derivative based method, and then there are also called inexact methods, will not which we'll not do today. We'll only focus our attention on these two, uh, in these two types of methods, or these two types of algorithm, that is and derivative free and derivative based. So as the name indicates itself, that derivative free means a method in which we'll not use uh, derivatives, and or the differentiations will not use, and second is derivative based, in which use the first order, second order derivative. So we'll see. So let's start with the derivative based methods. Before starting based method, let's define our problem and define some definitions that we'll use in our future in learning these algorithms. So first, let's define. So we are let phi is phi with the function let phi with the function with one variable or one scalar input, and it's a real value function. Then the problem we are looking at is minimum over x phi x. We are trying to uh, find this. So let's take an assumption. Let x star be the minimum, be the point at which phi x is minimum. This can be written mathematically as argmin over x phi x. Okay, so these are two equivalent statements. So we'll from now on use this statement when we have to write the above statement. Now, and we'll also assume let x star belongs to some closed set a comma b. Okay, these are the two assumptions for now. Now let's define something called unimodal functions. So unimodal functions. So a function phi is unimodal on a closed set a comma b if let there be 2 points x1 and x2 between a and b, and x2 less than x star, where x star is the minimum at the point at which phi x takes its minimum. If x2 is less than x star, then phi x1 is greater than phi x2, and if x1 is greater than x star, which means both x1 and x2 are greater than x star, then phi x2 is greater than phi x1. So this is the mathematical definition of a unimodal function. Let's look at these functions visually, or their graphical picture. So let's say this is a function, okay, and this is the, so if x1 and x2 are 2 points between a and b, and x1 and x2 are such that x2 is greater than x1. So let's say we find some point x1 here, then x2 should be greater. So this is true, right? So if x2 is less than x star, x1 and both x1 and x2 are less than x star, then x1 here is greater than x2, correct? Similarly, if x1 is greater than x star, then x2 is greater than fx1. So fx2 is greater than fx1. So this is a unimodal function. This is an example of unimodal function. We can have a similar function such that let's say this is the function that we have. Then if you look closely, this is b and this is also x star. Okay, so if this is x1, then x2 is greater than x1, then this. So we can see that again x1 is fx1 is greater than fx2. Correct. So these are two examples of unimodal functions. So what are not unimodal functions? What are some examples of non-unimodal functions? So let's again make a graph. So if a function is like this, where minimum, its minima is here, then this is not a unimodal function. Why? Because one counter example is if x1 is greater than x2, then in this case fx1 is not less than fx2. So this is not a unimodal function. So you can see that in unimodal functions there is a unique minima, and we'll use this assumption in all of our algorithms, that the function is unimodal initial in the initial interval that we are choosing. So with that, sorry, this is not unimodal, correct? So yeah, now let's move ahead. And now look at our first algorithm, which is let's look at our first type of algorithm for derivative free methods. So the problem we are solving is f is a function from R to R, and we are minimizing f over x, f over x. Now there are three types of uh, uh, algorithm in derivative free. First name is dichotomous. The second algorithm that we'll see is Fibo, Fibonacci search. And the third is the one which is most commonly used in single variable optimization, is golden section search. So yeah, so these three algorithms we'll see what is the algorithm, what are the benefits, and what are the disadvantages of each algorithms, and so on and so forth. So before starting dichotomous search, let me explicitly write a few assumptions that we are assuming. So let me reiterate the derivative free method. So we want to look at some algorithms in which we want to optimize this problem statement, in which the function is a single variable real valued function in which input is a scalar, and there are three main algorithms for solving this. First is dichotomous search, second is Fibonacci search, and the third is golden section search. Among these three, golden section search is the most common. We'll see why that is the case, and when we'll discuss golden section search. Now, before with dichotomous search, I'll just explicitly mention two assumptions that we are making in all these three algorithms. So the first assumption is before the starting the algorithm, we'll always get a interval which contains the minima of the function. So this will always get, this is an assumption. So basically, interval of uncertainty. So this interval is called interval of uncertainty. Um, a comma b is given initially, and it contains minima. So you may think, if I already know the minima, then why, like, if I already know the interval, why are we even looking at the algorithm? So sometimes it happens that we don't know the exact location of the minima, but we more or less know the interval, or a large interval in which the minima exists. So that is necessary. And the second point is that fx should be unimodal in a comma b. So what unimodal means, we already discussed. I'll just go up. So this is the definition of unimodal, that if the function phi is unimodal on a comma b, and we find any 2 points x1 x2 such that x2 is greater than x1 between a and b, then if both x1 and x2 are smaller than the minima, then phi x1 is greater than phi x2, and is both are greater than the minima, then phi x2 greater than phi x1. So, and these are some examples of the unimodal we already discussed. So these are the two assumptions. Now let's proceed with dichotomous search. So dichotomous search is one of the most basic algorithm that will come to your mind. So the basic idea behind this is, and before the basic idea, let me just ask you a question. So let's say this is my function, and this is my interval. So so let's say I try to find the a point, lambda here. I arbitrarily select a point lambda, a third point, a, b, and lambda, and try to use this information to get nearer to the minima. So can I use this information in any way if I know the function value at lambda? So please note, you actually don't see the fx, you only see, while algorithm you only see the x. So actually a single point will not give you much information. But if I add one more point, let's call it mu, then the and I know its functional value, then I can use this information. uh, so basically, if f mu is greater than f lambda, then what I'll do is I'll take this interval a to mu. I mean, from a to b, I'll take the next system to a to mu, next interval to be a to mu. So which can ensure that a to mu also contains the minima, and now uh, I have reduced the size of the interval. Now if f lambda is greater than f mu, note that we are choosing mu and lambda such that lambda is less than mu always, and they are between a and b. Okay, so if this happens, then we can take the next interval to be lambda and b. So this is a very simple concept. So mu prime, lambda prime. So let's say here we get, you can also think that what if lambda and mu are on two different sides of the minima, then also this procedure works. Um, then also this procedure works. You can take some time and think about that. So let's say I have only taken two examples in which lambda and mu are on each side of the minima, but if they are on two different sides of the minima, then also this procedure will keep the minima inside the interval. So with this basic idea, I'll explain you what we do in dichotomous search. So I'll just copy this. Wait. So we knew that we now know that if we have two arbitrary points between A and B, we have a algorithm uh, to iterate and reduce this interval of uncertainties. But how do we get this point? So first point that we get is, let's say find the midpoint of uh, let's say find the midpoint of the interval. So m is a plus b by 2, and then we have some small number epsilon which we add and which we subtract and add uh, to midpoint. So m minus epsilon, this is m plus epsilon, and we'll call this lambda and we'll call this mu. So if and now the procedure remains the same. This is how we get. So in the first iteration, if f lambda is if f mu is greater than f lambda, then the next interval will become a to mu, and if f lambda is greater than f mu, next interval will be lambda and mu. So this dichotomous thus tells us how do we how do we find those 2 points inside the interval. Now once we, let's say this is our new interval a comma lambda, a comma mu, sorry. Now we'll again find the midpoint. Let's say here, midpoint plus epsilon, midpoint minus epsilon. Now we'll see uh, um, we'll find, look at this condition, and then again we can reduce this interval to this point. So after several iteration, you will find that uh, your interval of uncertainty will stop when the interval of uncertainty, that is b minus a, length of the interval of uncertainty, it becomes less than your tolerance level. So this is a very simple algorithm. That's how we try to find the uh, minimum of a single variable real valued function. Now uh, let us look at look in some insights of this algorithm. So if you see at each iteration, the interval of uncertainty, let length of interval of uncertainty, like let's call it ik. So basically this tells us uh, the length of interval of uncertainty at the kth iteration. This becomes half every iteration. So basically it means that ik plus 1 is approximately half, not exactly half, because there is an epsilon involved. If epsilon is very less, then this is almost becomes half. So that almost half, like not exactly half because we have that epsilon there, but it almost becomes half at each iteration. The second insight is, which is actually a disadvantage, is that at each iteration, so you have to evaluate the function twice. So two function evaluation. So at each iteration you are doing two function evaluation. So for example, let's say you do n iterations, you'll all you'll end up doing 2n function evaluation. So and if evaluating a function is computationally heavy, let's say, then it can be a disadvantage, and it may take a lot of time. So that is one disadvantage that we have in dichotomous search. Even though it's a very simple and intuitive algorithm, this is one of the disadvantage that we'll try to solve. So this is the disadvantage that we'll try to solve in our next algorithm. So our next algorithm is Fibonacci search. So we'll explain later why its name is Fibonacci search. First, let's look at the basic idea behind the algorithm. So let's say this is our interval A and B. Okay, and these are the two internal points, lambda and mu. Okay, now there are two possibilities. One is we'll select in the next iteration, we'll select uh, this interval, or the next iteration we'll select this interval. And what do we do? We call this A1, B1, lambda 1, mu 1 in the first interval, and then this can be called A2, B2, or A2, B2, I mean depending upon uh, what is correct. So let's say if this will happen if f lambda 1 is less than f of mu 1, and this will happen otherwise. So if f lambda 1 is greater than f of mu 1, I hope I'm correct here. Yeah, this is correct. So this is what will the next iteration will look like. So let's say this is kth iteration, this is k plus 1 iteration. What we were doing, what now we'll again find a midpoint, one epsilon plus and minus, and this requires two function evaluation in each step. So we'll find the midpoint, it's epsilon plus, epsilon minus in both the instance. Instead of that, we can use the extra point that we had from the previous iteration. So let's say if the if this iteration is if this interval is chosen, then let's call it interval 1, then we have a lambda 1 point whose which we have already evaluated function at that point. We already know f lambda 1 in the previous step. And if this interval is selected, let's call this interval 2, we already know mu 1, correct? So we can reduce the number of evaluations, function evaluations in each step. So for in the first step, we'll require two evaluations anyways but in the further step we can do uh, we only have to evaluate the function once, correct? So this is so this idea we can use. This is the basic idea behind the Fibonacci search, and we'll see how do we use this lambda 1 and mu 1 in the further iteration. So this is the basic idea. let's move on to uh, uh, define define it. So basically what it means that we already have f lambda 1. We just have to find some point, extra point, uh, apart from the any point that we have, and we can go on to the next iteration. So one natural question is how to find that next point that we'll look at. So let's say this is the initial interval of uncertainty AB again. Let's call this A1 and B1. Let this be lambda 1 and mu 1. One assumption that we'll make here is we'll place them initially in such a way that they are symmetric. So lambda 1 and mu 1 are placed in such a way that they are symmetric. So what does that mean? Means which means b1 minus lambda 1 equals mu 1 minus a1. This is what it means. So basically this equals this, and same, and in the same way we can also write lambda 1 minus a1 equals b1 minus mu 1. Okay, so this is what symmetricity means here. So I'll just rub this off. Now so let's divide it into further. Let's say it gets divided into uh, some interval. And okay, so we'll call the new a2, which is a1. So if this condition is true, which means f lambda 1 is less than f of mu 1. If this condition is true, then this will happen, and f lambda 1 is greater than f of mu 1, then this will happen. So here a2 will become a1, b2 will become mu 1, correct? And this is the lambda 1 from our previous uh, from previous and from previous iteration, and let this be mu1 from previous iterations. So here also, if the second condition is true, then a2 is equal to lambda 1, b2 is equal to b1. Okay, one more assumption that we'll take is or assumption or necessary for this condition is we'll assume the new lambda 1 to be uh, mu1, mu2 equal to lambda 1. This will assume here also lambda 2 is equal to mu1. Okay, let me just correct the. So okay, so yeah, these are the two assumptions that we'll take, that we'll place lambda and mu symmetrically, and after each iteration, if lambda 1 remains in the interval, then we'll convert that into mu 2, and if mu 1 remains in the interval, then we'll convert that to lambda 2. So these are the two assumptions that we take. I'll write it explicitly, assumptions. And once we these points, at these points we already know the functional value. we just have to find one more point on the left of lambda mu2, that is we want to find lambda 2 here, and on the right of lambda 2 will, which means we have to find mu2. Okay, so this is the next question: how do we find these 2 points? And you already can visually see that at each iteration here we only require one function evaluation, correct? Yeah, so we'll move ahead. And before answering this question, so we have a very obvious question: how to find second point in interval. Correct. So we'll answer this question, but before that, we'll try to derive some relations between the length of the intervals. So yeah, so the next I think is relation between length of intervals. Okay. Okay. So once again the same diagram. Let's say this is A1, B1, and these are lambda 1 and mu 1. So let's say in the first case this gets selected, or I mean the values were such that this became the next interval. This is A2, B2, this is lambda 1, which is actually mu 2, correct? Hmm. And then let's say by some algorithm which we have not derived yet, we find a new point, lambda 2. Okay, we find some new point lambda 2, and we go one step further, and let's say this time around the values were such that the interval remained only A2 to mu 2. So now this will be called A3, this will be called B3, and we have lambda 2 here, which we can write as mu uh, 3 is equal to lambda 2. And we again find a point on the left of this previous point. Okay, so let's call this iteration k, or let's call this iteration I1, let's call this iteration I2, let's call this iteration I3. So here what I mean by iteration is I1 is the length of the uh, interval of uncertainty, that is I1 is equal to B1 minus A1. Okay, now if I1 is equal to B1 minus A1, I1 can also be written as B1 minus mu1 plus mu1 minus A1, correct? And if you look closely, mu1 minus A1 is actually length of interval 2 here. I1 is equal to B1 minus mu1, and mu1 minus A1, that is mu1 minus A1, is same as the interval to 2's length. So we can write it at interval length of interval 2. Now B1 minus mu1 can be written as, we already saw, because we have assumed the symmetricity condition, that is here you can see that B1 minus mu1 is this length, which actually is same as this length, because lambda 1 and mu1 are placed symmetrically. We already saw that. So we can write this as lambda 1 minus a1, which turns out that is equal to the uh, length of I3, correct? So I1 is equal to I2 plus I3. So this is a very important relation. So if we assume symmetric conditions like symmetric placement of lambda and mu, and also assume that after each iteration mu2 will become lambda 1 and lambda 2 become mu 1 based on the conditions, then by these two assumptions we can prove that the current length of the interval is equal to the sum of the next two sum of the intervals. So this is a very important relation, and you may say that I just chose a, a single interval in each. So basically, in the first iteration, I chose a1 to mu1, but if I choose lambda1 to b1 in that case, so it turns out that because of the symmetric placement of lambda1 and mu1, a1 mu1 length is equal to lambda1 b1 length. So and so on and so forth. So you'll get in all the permutation and combinations of the intervals that you get, you'll always end up with this relation I1 is equal to I2 plus I3. You can give it a try yourself, but that is the case. So, and this you can write uh, for any interval. So I1 equal to I2 plus I3, I2 equal to I2, I3 plus I4, and so on and so forth. So I can write In equal to In plus 1 plus In plus 2. So this is the relation between the intervals. Now I'll make one more assumption that will make our life very simple. So I'll assume that In plus 2, length of In plus 2 is 0. So what do I mean by that is length of n plus 2th interval is 0. So what do I mean by that is, let's say I have an initial interval of AB. I keep on reducing it. Uh, First I reduce it to this length, then I reduced it to this length. And there will come a point where AK and BK, the lambda will be absolutely at the midpoint of AK and BK. We are assuming that at n plus 2th step, the lambda k will come at the center of AK and BK, such that if you find mu, it will coincide with lambda k. So and after a few steps, you will not get so the length of the interval will become 0. So that is what we are assuming here. You'll see why we are assuming it. Assuming that. So because of this assumption, let's see what what happens to the other lengths of the intervals. So what will n plus 1 become if in plus 2 is 0? So in plus 1 is equal to in minus in plus 2. So it is actually 1 dot in. So basically it's in plus 1 same as in. Now what is in? So it is in plus 1 plus in plus 2. This will also be same as in. But now what is in minus 1? This will be um, in plus in plus 1, which means it is 2in. What happens to in minus 2? In minus 1 plus in, which means it becomes 3in. So as you can see, this becomes some kind of a series, and if you look closely, each term from here onwards is a sum of previous two terms. So the next will be 5in, then it will be 8in, and so on and so forth. So this is actually Fibonacci series. Um, so in minus 3 plus in minus 2. So this is a Fibonacci series, and that's why this because of these assumptions, and because of this series that pops out in this search method is called Fibonacci series. Okay, so this term is called Fibonacci series. So we can write like this. This is the f naught term of Fibonacci series, f naught into in, f1 into in. So let's just formally define the Fibonacci series once so that this becomes easy. So Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, 55, 89, etc. Right? So where fk is equal to fk minus 1 plus fk minus 2 for k is equal to 2, 3, and so on, and f0 is equal to 1, f1 equals to 1. So f naught f1 are given 1 and 1, and f2 is given by this formula fk is equal to fk minus 1 fk minus 2, and for all k greater than equal to 2 this formula is used. So this is what Fibonacci sequence is, and with that we can write these terms also: f2 dot in, f3 into in, and so on and so forth. Now let's try to look what is the general kth interval would look like. So general kth interval would look like ik plus 1 plus ik plus 2, correct? And it turns out it will look like n minus k plus 1 in. Take a moment to understand why, how could I write this. uh, so basically if you say for n plus 1 f0 was there, n f1 was there, n minus 1 f2 was there. For k it will be n minus k plus 1. This k plus n minus k plus 1 is n plus 1, and same is true for all the previous indices. And here also it will be fn dot in, correct? So this is how Fibonacci terms are there, and we can use this relation, the final relation, that is I1 equal to fn dot in, to see how uh, I, uh, the length of intervals changes after n iterations. The interval will become in equal to I1 upon fn, correct? So basically if we use these assumptions, then the nth interval, length of the nth interval will be the corresponding Fibonacci term, uh, 1 by 1 divided by the corresponding Fibonacci term into the initial interval. That will be the interval reduction after n iterations. So let's say I have n equal to 10, then this will be the reduction. So you can see after 10 iterations, number of function evaluations, how many they will be. So in first iteration I will evaluate the function 2 times, and subsequent iteration I'll e- evaluated one per iteration, correct? So which means 2 plus 9 equal to 11 iterations. So function evaluations are 11, correct? And uh, what is the reduction in the interval of uncertainty? So if you divide I1 1 by 89 is comes around to be 0.0111. So let's say 1%, approximately 1%. So you reduce in 10 iterations, you reduce the interval of uncertainty to 1%. But the number of function evaluation that you did were 11. Please remember, for dichotomous search in 10 iteration, you would have required 20 function evaluations. So this is the benefit of Fibonacci sequence here. But there is also a disadvantage, which somehow is very obvious here. So we should know. So let's say we want to find a minimum with some tolerance. So we are given a tolerance. So we should be able to find n with that tolerance. Basically, n means the nth, because we want to know the nth Fibonacci term. So we have to find the uh, nth term to know to use this algorithm. We'll see in the example what do I mean by knowing n here. So yeah, so that's the disadvantage, that we should know n beforehand. Okay, so yeah, n beforehand. Now let's look at how to find. We asked a question previously, this question here. How do we find a second point in the interval using Fibonacci series? Let's try to answer this question. How to find the second point in the Fibonacci series? So let's say this is our interval again. And this is lambda k, this is mu k, this is ak, bk. Let's assume this is the first interval reduction that we got. Okay. Let me just. So this is AK plus 1, this is BK plus 1, and this will be lambda K plus 1 equal to mu K. Okay. Now let's say we find some mu K plus 1 here. Okay. So how do we find that? So given that we have assumed symmetricity, that is this length is equal to this length, and so this length is also equal to this length, and we want to maintain this symmetricity in every iteration, this length equal to this length. Now if in each iteration we know a lambda k plus 1, we add this length to ak and we'll get mu k plus 1, correct? So basically in each iteration we'll find bk plus 1 minus lambda k plus 1 and add this to ak plus 1. This is how we'll get mu k plus 1. this might be very obvious, but there is one problem with this, that how do we know? Because in each iteration we have one of the points, correct? But in the first iteration we do not have any point. So how do we select the second select the points in the first iteration? That is also question. So this is good for kth iteration, but how do we select the points in the first iteration? So yeah, so for that let's try to write this. So ik equal to f n minus k plus 1 dot in. This is true, correct? Now let's say ik plus 2 is equal to f uh, n minus k minus 1 dot in, and ik plus 1 equal to f n minus k dot in, correct? So ik plus 2 by ik plus 1 equals fn minus k minus 1 upon fn minus k, which will give us ik plus 2 equals fn minus k minus 1 upon fn minus k dot ik plus 1. So this is correct. Now we want to know I2 and I3, correct? So let's put k equals to n minus, or k equal to uh, let's put k equal to 0. Then I2 equals f n minus 1 upon f n dot I1, where I1 we know, so we get that b minus a interval. So I2 can be written in this way. And what is I3? I3 will be fn minus 2 upon fn minus 1 into I1, I2. So this is I3. Okay, so the first interval we know, and if I2 we already know, A, B, A1, B1, and we all know that I2 will be something here, A2, B2. Then we can write mu1 equals A1 plus I2, and mu2 equals, or sorry, lambda 1 equals b1 minus I2. So in this way we can get 2 points. But please note here that for each given I1 and each given tolerance, we have to know n beforehand for knowing I2, or for selecting the first 2 points. So that's what I was talking before about the disadvantage of this, and disadvantage of Fibonacci sequence, that we require to find n beforehand. Now, to solve this issue, uh, there is a one more algorithm called golden section search. Okay, so what is golden section search? So this is a limiting case of Fibonacci. Okay, and in this case, n is not required beforehand. So we previously looked at this relation. That is, let's copy it. Fibonacci. Because I2 is equal to Fn minus 1 upon Fn into I1, that's why we require this n beforehand, so that we can calculate Fn and Fn minus 1 and hence determine first lambda and mu in the first 2 points inside the interval. We can, so this is the reason why n is required beforehand. We can remove this if we limit this to I2 equal to some constant r times I1. And let's do this for um, all the interval lengths. I.e., I can write it ik upon ik plus 1. Sorry. So this is, so let's look at it at here. So ik upon ik plus 1. So basically for Fibonacci series, ik upon ik plus 1 is equal to f uh, n minus k plus 1 upon f n minus k minus 1. So yeah, so this is the relation for Fibonacci series. So, and it changes with every k. So we assume it to be constant in golden section. So ik plus 1 upon ik plus 2 is equal to so on is some ratio r. Now let's try to find this ratio. So we know ik upon ik plus 1 equals uh, r, implies ik and ik plus 1 upon ik plus 2 equals to r. This implies ik upon ik plus 2 equals r square, and ik upon ik plus 3 equals r cube. And we also keep the assumption that I k equal I k plus 1 plus I k plus 2. So this is from Fibonacci search. We keep this assumption. Okay, so we'll divide it by ik upon ik plus 2 equals ik plus 1 upon ik plus 2 plus 1. This can be written as r square equals r plus 1, which becomes an equation, a quadratic equation, which needs a solution. And it turns out that the solution to this quadratic equation is 1 plus root 5 by 2. And we are ignoring the negative root. Ignored because it's meaningless, right? It doesn't mean anything. This is approximately 1.61803 dot dot dot. This is somewhere there, and this is called golden ratio. This is called golden ratio. That's why, hence the name golden section search comes from here. So that's why golden section search, its name is golden section search. And as you can see, add some insights. So each iteration is independent of n, and also uh, initial 2 points is not dependent on n. So basically this means is you do not need to find n beforehand, and that is very helpful. And the length goes on decreasing as a GP. So first interval length is I1, then it will become I1 by R, I2 by I1 by R square, and so on and so forth. So it becomes a GP. And if for nth interval, so let's say IN interval for golden section search is given by I1 by n, sorry, r to the power n minus 1. So this is the nth interval length. Now let's compare this to Fibonacci. Okay, let's compare this to Fibonacci. We saw that nth term for golden section here is I1 by Rn minus 1. We also saw previously that nth term for Fibonacci is I1 by Fn, where Fn is the nth term in Fibonacci series. So um, it turns out that for large n, Fn can be approximated as r to the power n plus 1 upon root 5. This is a standard result that you can see online. I'm not going to prove it here, but this is what a standard result is, that nth term can be approximated as r to the power n plus 1 by root 5 for very large n. Then I Fibonacci series, the term goes to r n plus 1, and where r is the golden ratio here. So r is the golden ratio. So this is golden ratio. Okay, so now if we compare IN of golden section search and IN of Fibonacci search, you'll find that it comes out to be added by n minus 1 upon root 5 Rn minus 1 comes out to be r square by root 5, which is around 1.17. So which means that the interval length of golden section is 17% more than the interval length of nth interval length of Fibonacci. So Fibonacci sequence is a more tighter one, but um, there is a trade-off that you get. You don't have to find n beforehand in golden section search. So this is the benefit of golden section search. Now we'll look at some of the algorithms um, in MATLAB. So now let's look at some of the examples, programming examples in MATLAB of the algorithm that we have learned today. So here is a file known as testing environment in which we'll test our algorithms. So here is the function definition. So function, it's a polynomial function in one variable, basically 1 by 4 x to the power 4 minus 5 by 3 x cube minus 6x square plus 19x minus 7. So this is a polynomial. Its minimum occurs at somewhere around minus 2.56 and so which we will try to find. So here interval of uncertainty, the first interval of uncertainty is minus 4 and 0, and its length is 4, and the tolerance with which we want the correctness is 0.001. Correctness in x that we want is 0.001. So first algorithm that we'll test is dichotomous search. So here the function that runs, it intakes the function definition, the first interval of uncertainty and the tolerance, and gives you the minimum value, the iterations and the function evaluations, and some rest of the arrays which are necessary for like data plotting. There is Fibonacci search also and golden section search also, which we'll look at later on. And right now they are commented. And then there is a function display result which displays the results in a tabular manner. So let's look deeper into the dichotomous search first. So this is the dichotomous search function definition, and as we saw that it intakes function definition and initial interval of uncertainty and tolerance. So first, because it's a very simple algorithm, so it won't be difficult to understand. So we define some initial variables to count iterations and number of function evaluations. Then there is epsilon. So here you can look, the epsilon is smaller than the tolerance which is necessary. Then we start a loop in which we check that if the interval of uncertainty is greater than tolerance, then we'll continue the iteration, otherwise we'll stop. We find the middle point. We will find lambda uh, by midpoint minus epsilon by 2. We find mu midpoint plus epsilon by 2, and based on these we see if f lambda is less than mu, then we change the interval of uncertainty where b equal to mu, or else a is equal to lambda. And then we continue this iteration, we increment the iterations and function evaluation. Here notice that function evaluation is getting incremented by 2 because we have used two function evaluations in each iteration. And at the final we give the minimum to be the smaller, the final minimum is given by as the midpoint of the interval of uncertainty, the final interval of uncertainty. Now let's see how does it work in testing environment. So yeah, so let's run testing environment. So this we ran. So you can see, let's verify some of our insights that we saw. So this is the minimum that we got, minus 2.56. This is the value of the function at that minimum. So it took 13 iteration to get that tolerance, and to get the minimum value under that tolerance. And look at this, the function evaluation is double the number of iterations, just as we saw. Now here's the at each iteration, what are the A's and B's, or what are the interval of uncertainty. Now let us look at the length of the interval of uncertainty. The first it was -4 and 0, so basically the length was 4. Now in first iteration it became approximately 2, then 1, then 0.5, 0.25. So this was one of our insights, that at each iteration the length of the interval becomes half. So that we verified here. Now let's go on and see the Fibonacci search. I'll just uncomment it once. Rest of the things remain same. I just uncomment Fibonacci and comment out the dichotomous search. Now let's look at Fibonacci search. So it's a similar structure. The structure of the function is similar. It takes function value a and b and tolerance. Now, if you can see in the first step, we try to calculate n. So the calculation that here it is done is a little bit complicated, but overall what it's trying to say is, so let's say you get some interval a and b, and you want to find the n based on that, because we know that we want to assume the first 2 points, lambda and mu, using this. So the n, how it calculates the n is, like, we know that the final interval in will be initial interval I1 by fn, and this should be lesser than the tolerance. So based on that tolerance, we try to find what the n is, and once we get n, then we try to initialize the first few points. So here it is written. So we know that the relation between the first and the second interval is fn minus 1 upon fn, and the relation between I3 and I1 is fn minus 2, where fn is the nth term of Fibonacci series. So fn minus 2 upon fn, and lambda is basically a plus I3, or length of the third uh, I3, and mu is a plus I2. Actually, lambda can be also written as b minus I3, but they are basically the same. Here, this is just code written for initializing the initial value of lambda and mu, which we already saw. Now, in the iteration, we start the iteration. If f lambda is less than f mu, uh, then we change a bunch of stuff. B becomes mu, mu becomes lambda, and new lambda is a plus b minus mu. And we use the previously saved function value of f lambda and put it to f mu, and we evaluate f lambda by function evaluation. So you can see there is only one function in evaluation here. I'll also comment it here. Only one function evaluation. Okay. Same is the case when f lambda is greater than f mu. Similar kind of thing, but in a slightly opposite manner. So I'll write this here as well. Okay, so we increment the iterations and the function evaluations, and finally the minimum that we give is the minimum interval of uncertainty. Like, so we do one step dichotomous search here, and this point, and hence we give the minimum. Let's see how it works in our testing environment. Yeah, so as we can see, this also gave a similar same minimum point, its same value. Look, but look at the number of iteration. It's 16. So previously we saw it was 13 in dichotomous search, but in Fibonacci series it's 16. Uh, but look at the function of evaluations, number of functions evaluation, it is only 18. While on the other hand, in dichotomous search, it was 16, double the number of iteration. Even though the number of iterations had increased, the number of function evaluation is still less. It's just 18. So yeah, so that's the case. So that is one of the insights that we looked. Now let's look at the golden section search. So golden section search, the structure is again similar. FAB tolerance. Now first we calculate the golden ratio, which is 1 plus root 5 by 2. So it is calculated here. And then we try to initialize the initial points, initial lambda and mu. So length of initial interval is b minus a, and length of the second interval, which by golden section search we already saw, is 1 by golden ratio into I1. And lambda can be given by b minus I2, and mu can be given by a plus I2. So these are the initializations of lambda and mu. So rest of the things are same. It's actually same as Fibonacci series. Only the difference is at this point the updation of lambda is uh, is different from Fibonacci search. Only this is different from search, Fibonacci search. The rest of the things are same. So let's look at how this performs in testing environment. So yeah, so it already also gave the same minima and same number of same value of function. But as you can see, the number of iterations here have increased than golden section search. So has increased than Fibonacci search, and corresponding function evaluations have also increased. The reason for this is that we discussed that the final interval of uncertainty for large n is for the golden section search is 17% larger than that of Fibonacci search. So because of this difference, it takes a slightly more number of iteration to get the same tolerance level in golden section search than in Fibonacci search. That's why it took a little bit more number of iterations. That is 18 as compared to 16 for Fibonacci search. So yeah, so this programming example helps us realize to verify all the insights that we learned. Now let's go back to pen and paper. So we till now we did derivative free algorithms. We'll now do derivative based algorithms. So the two types of algorithms that we'll study in derivative based is bisection method and then Newton method. We'll study bisection today and then Newton will complete tomorrow because of I think the lecture is getting longer. So what is bisection method? So it's very similar to dichotomous search. So what we do in this is uh, uh, so we will again assume that our function is unimodal in a given closed interval AB. Correct? This is assumption. The second assumption is f, the function that we have to optimize, is continuously differentiable. These two things we have to find. It is similar to dichotomous search. Okay, and the idea behind this is let's say I have a curve. I find the midpoint and see the derivative at this point. If it is positive, that is f dash c. If it is 0, then c is minima. Correct. If f dash c is greater than 0, then new interval will become a comma, let's call this c, where c equal to a plus b by 2. New interval will become ac, and if f dash c is less than 0, then new interval will become cb. So in principle, this is very similar to dichotomous. It's just that we do not need 4 points here, only 3 points, and the derivative at that point will work. So here you can see we have to calculate the derivative at that point, which means that's why it is a derivative based method. So yeah, so we'll end our lecture here today. We define what are derivative free methods, like dichotomous search, Fibonacci search, golden section search, and we also defined we also explained one of the derivative based algorithm called bisection methods, and Newton's method we'll do in the next lecture. So till then, uh, that's for now. That's up for now. We'll meet in the next lecture. Thank you.